Good afternoon, everyone. I'm by names of Katende Roni Magala, and I'll be taking you through our project, which is called Graph-Based Large Acoustic Reasoning Model for Multi-Patient Target Sound Extraction and Respiratory Monitoring in Resource-Constrained World. Specifically, this project is all about determining the respiratory sounds and then figuring out it's used in determining which patient, like it's going to be used in words and determining which patient specifically has a respiratory problem. That's what we are specifically dealing in. Is this patient okay, we are dealing with the respiratory sound, like the breathing rate. Let me say that if the patient is breathing faster, or the breathing has some whistles or some crackles, yeah, that's what we are determining most. So that we are able to help those patients that are suffering in a stressful condition. They easily be reached. Yamnet, the which are what acoustic features that are able to learn from acoustic features without requiring manual feature engineering. Let me say, yeah, going further. Yeah, let me first take you. So we have the wait. Yeah. We have the target sound extraction. Target sound extraction, specifically, this shows how most sound is going to be extracted, or isolating a specific sound of interest. Let me say that I want to isolate all the background noise from these whistles that I'm going to collect, the whistling sound and the crackle sound. So we shall be using the target sound extraction. Then we have the knowledge distillation. Let me say that this is kind of a model compression technique whereby a large model is compressed, or a powerful model is compressed, or let me say like a teacher model is compressed in terms of to learn, okay, is compressed or is transferred into a learning knowledge, and a learning knowledge a smaller model, like a student model. So we shall be using this, yeah. Then we have the what? The multi-patient monitoring. The multi-patient monitoring here specifically involves continuous tracking of respiratory conditions for multiple patients. We are able to monitor how are the breathing rates, or how are they going to be. There are going to be some crackles of a particular patient. Yeah, we shall be monitoring patients to see their breathing rates, yeah, mostly that. Then the explainable AI. Explainable AI refers majorly to the development of machine learning systems whose decision-making process can be understood and interpreted by humans. Yeah. So going further, let me what's all about introduction. Introduction, okay. Serious. There are very many people. I can't be able to monitor a lot of people just because, okay, like how their breathing rates, how are they going to be able to, like, how am I going to manage each and every person's breathing rate? So here, that's why we have some shortage of medical personnel, limited monitoring equipments, and and like a noisy word. So if at all like there is a noisy word, yes, if at all there is a noisy word, that means that I won't be able to hear the crackle of a person who's on the other side of the corner, or of the patient who's on the other side of the corner. Such manual processes take a lot of time, are time consuming, and only time consuming, but also prone to the errors. Like, I might hear the crackle, then I kind of search who has coughed or who has made that crackle breathing. Yeah. So I might fail to identify the exact patient. So here we are able, this project majorly proposes an intelligent and scalable solution by leveraging the large acoustic models, target sound extraction, and graph neural networks. Like, specifically, this project will be able to determine, or will be able to use the large acoustic models to be able to, we are going to use the large acoustic models to listen to those sound, and then the target sound extraction to determine only the specific sound required, and then the graph neural networks. Like, this graph neural networks basically focuses on so much graphs. Let me say that I'm moving on a steady progress. Then a crackle is made. That means that that graph will rise rapidly. That it will notice that this patient, or like, there has been a crackle or a sound made, which is an abnormal sound, an adventitious sound. A system that can isolate and identify. Yeah. So that's a brief introduction. Then the background. Let me say, there is scarcity of specialized medical equipments in the hospital. Like, we have limited monitors, or we have limited like microphones. Actually, even in some hospitals, there are no microphones that can be able to hear these these noises, or like able to determine which significantly hampers the effective management of patients with respiratory sickness such as asthma. We shall need those systems that are able to classify that this person who has made this crackle has pneumonia, this person who has made this crackle or whistle has asthma, has tuberculosis. In most wards, only a few functional monitors are available, like requiring health workers check vital signs such as the respiratory rate at intervals and records them on paper charts, which often led to missed detections. So specifically about this, like, it shows how the manual processes, or the manual labor, is time costing, and there are the limited equipments to monitor the patients, who have respiratory sickness. So I shall take you straight away to the literature review. We have some papers like this paper one of waveformer streamline. This one specifically focuses on a transformer-based real-time target sound extraction. Like, is it able to isolate? This paper specifically was all about target sound extraction. How are these models able to isolate sound, like the background noise, that unwanted noise, from the sound that we required? Then now, like, the limitations that I found while reading this paper, like, they tested it it limits the model to do what? To focus so much on the real world problems. We have the Castro Opnima graph-based audio classification. This one majorly proposes a novel approach for environmental sound classification by representing audio data as graphs. Okay, like, first of all, this paper occurred in terms of sound classification. Let me say that those whistles and what? Whistles and crackles. Why am I giving whistles and crackles? Because specifically these are the respiratory. Okay, crackles, that is the high, like, let me say that a person, if he coughs or he breathes, that sound that comes, then crackles, that pop-up sound like that comes out after coughing. Then the proposed, this paper specifically proposes so much on the sound classification, whereby it can classify that this cough was specifically for pneumonia. This cough was specifically for tuberculosis. The coughing rate of a tuberculosis patient is not the same as this person who has normal cough. Yeah. Then the limitation that I found, and it's able to form those graphs specifying or classifying that this was like the tuberculosis was higher than the than the coughing of pneumonia, higher than the coughing of asthma, or like that. Then the method relies on manual constructed, like this method, the limitation, it relies on manual constructed graphs and does not explore adaptive graph construction strategies. We have the problem statement. Problem statement here, problem statement, like the domain application. In most Ugandan, like in many Ugandan healthcare wards, like there is limited resource, like there are limited resources, like the clinicians, the monitoring, the monitors, the microphones, and there are also no, like here at Kawempe, giving a reference, I have never seen, I took there my internship, like I carried out my internship from there. I have never seen them having microphones of this target sound extraction. Like they just use clinicians and those word, like the nurses and doctors, to be able to monitor the respiratory breathing of these patients. So we shall have the high background noise levels. Actually, there are a lot of engagements, or like a lot of noise within the background. Absence of multi-patient monitoring tools, limited medical personnel. Then we have the computational problems. Computational problems, these ones, like the source separation of like separating overlapping acoustic signals from multiple patients, and background noise. We have the feature extraction, computing, like in terms of computing respiratory biomarkers and rate rhythms from complex audio streams. We have patient attribution, correctly assigning detected sounds and anomalies to the corresponding patients. Then the graph-based reasoning, like in terms of modeling temporal and interpatient relationships to detect individuals and what respiratory. Yeah. Then we have the research objectives, research questions, like specifically we have the first one, which real-time anomaly detection algorithm be adapted to identify abnormal respiratory patterns in continuous hospital monitoring. Let me say, in terms of in real hospital settings, respiratory conditions can change rapidly. Patients may transition from normal breathing to whistling, crackling, or shallow breathing depending on their conditions. Therefore, an effective model must be able to process audio streams in real time, detect sudden anomalies, such as those crackles and the whistles, work continuously and reliable. Yeah. Then the second question was, what architecture are most effective for detecting deviations in breathing patterns? Architecture the large acoustic models, those already trained models on massive sound dataset, strong transfer learning. Yeah. How can large acoustic models be easily deployed on resource constraint? We know that in hospitals they they have limited resources, like lots of resource settings in terms of they might not have that powerful GPUs or continuous cloud connectivity. So the solution may be then training that high capacity models in the cloud, then compress, distill, and quantize them. We have those objectives like to derive respiratory patterns using MidTerm, like we're still continuing. This data set was specifically obtained from Hugging Face. Then it was able to, it contains a stethoscope recordings of 126 patients from various hospitals from different wards and clinicians centers. Like it was able to take recordings at a sample rate of 4 kilohertz and 16-bit resolution to ensure that the bootlow and high frequency were captured. So this data set specifically has 8 labels: the chronic obstructive pulmonary disease, pneumonia, and then the what? And then so we have the exploratory data analysis. This one was specifically taken using the what? Okay, we shall begin from the male spectrogram. Male spectrogram, this one focuses so much how those weasels or like the crackers were being determined. Then the feature coloration according to the MFCC, the centroid, and the ZTR, the means. So it shows that that the mean, MFC, and the ZR, they had a low correlation. Then the MZR and the M centroid had the highest correlation of 0.79. Then we had the outliers showing different labels or different features. Then we have this the waveform. We have the methodology of the proposed architecture of GLAM. So here, sorry. So data collection layer. So data collection layer, this one specifically, how was it able to collect data? Multiple channel audio streams, like, okay, since we had a Hugging Face, so it was able to collect that data from the Hugging Face. Then it went further to the pre-processing layer. Pre-processing layer in terms of noise suppression, band pass filtering, like filtering all the band passes and the noise suppression, like the background noise. Then the source separation layer. Then it went further to the multi-source separator time domain separation network and output K isolated audio streams. Like after that, it was able to output that clean data that we want. Then it went to the feature extraction. Is it able to determine like the crackles, or like what exactly do we need? Was it able to extract that noise? Because there are different breathing rates, but was it able to extract that exact breathing that we want, like the crackles and the whistles? Then it went further to the patient attribution layer that assigning each patient according to the, like, let me say that we have Ronnie here and we have Kathy here. Like it's able to determine which patient was able to what to exhale or breathe in or out, like, okay, like in an anomaly way. Yeah, then it went further to the reasoning and analysis. Reasoning and analysis, like baseline model, individual patient trends. Okay, like giving graphs that this patient was breathing in this period of time, breathing at this rate here. Then that anomaly detection layer, yeah. Then the deploy model, deploying it onto the GPU or like onto any server or onto the cloud. Then it went further, then alert interface layer. This is like building an interface whereby it's going to alert everyone, like this patient is breathing abnormally. Yeah, creating that dashboard. Yeah, that specifically was for the GLAM. Then we have the YAMNet. YAMNet, that's so far we have built. So we have this file, like the data preparation layer. As I say, that we get the audio files first, then we are able to perform the EDA. Then feature extraction. Feature extraction, like, is it able to extract that exact sound that you need, that you require? Like, it processes it, audio processing, then YAMNet model enhances the feature extraction, the STD pool, temporal end. Then we went further to the model training layer. Like, since it's a pre-trained model, we are just fine-tuning according to the data set that we gave it. Then we went to the evaluation layer. Yeah, evaluation, like performing those confusion matrix, the feature importance, like classifying reports, the recall F21. Yeah, then we deployment layer, like deploying the model onto the what? To the server, or like, so that you can be able to what? To access it. Yeah, so specifically we used this YAMNet, a pre-trained audio classification model, originally trained. Since it's a pre-trained, it was originally trained on a large dataset of over 2 million labeled sounds. YAMNet converts the respiratory audios into male spectrograms, mobile. Then in our project, like, it acted as a feature extractor. Yeah. We passed each breathing audio clip through YAMNet to obtain the 1,024 dimension embeddings representing the sound characteristics. So, in conclusion, this work specifically aims at developing a lightweight and real-time respiratory monitoring tool capable of automatically detecting and classifying abnormal breathing patterns in hospital patients by integrating advanced deep learning model and knowledge distillation techniques. The limitations that we conquered with performance is dependent on the quality and variety of the respiratory sound data, expenses to acquire hardware equipments for collecting data. Thank you very much. The next step will just be, we acknowledge Dr. Galiwango for his constructive feedback mentorship. Thank you very much. I remain as Katende Reni Magala.